Exercise 12E, 1 joule throws a stone into the air. The height of the stone can be modelled by the equation, this one, where t is in the time in seconds that has passed since the stone was thrown, and the function is the height of the stone in meters. So I've done this. The first thing that you should do with a question like this is put it in the calculator, have a look at the curve. That's about his height. Remember, he's throwing the stone, so it doesn't start at zero height. It starts at his height, where his arm height is, and he throws it up in the air, and it comes down here. Now, I can do a lot with the calculator. Once I've got it in there, I can also find the maximum point by using Analyze Graph, and I can find the point, and that's actually the end of the question. But what they want you to do here is to practice doing it without the calculator and without the calculator graphic functions. It says find the first derivative. So that's the equation there, and the first derivative of that is this. Remember, the derivative of a constant is 0. The derivative of this is 1. You think there's a t to the power of 1, basically, that is. So it's 1 down here. That's 1 times 7.25. T becomes t to the 0, which is 1, minus 2 times 1.875, which is 3.75, and the t here becomes 2 minus 1 at the top, so that would be t to the 1 power, which is t. B, find the stationary point and the time when this occurred. So what we really should be looking for is to see if we can find that. But if you didn't have the graphic display calculator, the way you find it is that we know that the derivative is 0 at a stationary point. So what we do is we equate the derivative to 0 and we solve for t. And we do that by putting 0 here, and that's our derivative function, and we solve for t and we get 1.93, and that's in seconds, 3 significant figures. Now, to find the actual point, though, that point, we also have to put it back in the original equation, the original function, to find the function value at that point, which is the y value. So we put it back in there, and we get 8.01. And so the coordinate point is 1.93 and 8.01. Show that this is a maximum point. Well, we saw this from the textbook. If it's a maximum, it's a positive slope, changes to a negative slope. And do we get that? Try values of t just to the left and the right of t equals 1.93. Now, we have to try this in the derivative function because the derivative function shows us the slope. So we put 1.9 into this, and we get a positive number. Because it's a positive number, it's a positive slope. So we're getting the positive slope. And we put the other number, which is just to the right of 1.93, and we tried 2. Right? And we get minus 0.25, and that's a negative number, so it's a negative slope, and that shows us that it's a maximum. Let's have a look at 2. A company's profits in thousands of dollars can be modeled by the function, this one, where X is the number of units sold in millions each week. Now, the first thing I did was just to put that function into the calculator to see what it looks like. The first image came up with like that on the graphic display calculator, and then what I did was I looked at the way it was displayed and I changed the numbers on the y-axis and I got it to look more like this so I could see where there might be minimums and maximums. Okay, so you can do the same on your calculator as well. Then what I did, it says sketch, so I then copied it onto my own one. In the test, you would just have to make your own graph and make sure that you put the label on there. Actually, I haven't got the units on here. I should write the units as well. Let me just add those. Okay, there we go. These are the critical things you need to do. You need to do where you need to you have to label the axis, put the units down, and make sure that you write down at least some numbers along here. You don't have to do everything. And if it goes through 0, it goes through 0. So wherever it crosses an axis, you should also write that point as well, and that's 0, 0. There. It's just the origin there. Okay. Okay, the other important thing to do is have a look at the restricted domain and make sure that you stop it at 15, right? That's 15 right there. You need to stop the graph at 15. You start the graph at 0, so you need to stop there. B, calculate the average rate of change between x equals 2 and x equals 3, including the units. Explain the meaning of the value you find. Okay, if you want to find the average rate of change, we have the x values because we know x is 2. So if you can look closely, there's actually a green straight line in there. It goes from x equals 2 to, when I put a 3 in here, to 3 on the graph. There's a straight line. Now, it follows the curve, but not exactly, right? Okay, so how would we find the average rate of change? Well, that's just the slope, and we use the gradient formula. y2 minus y1 y2 minus y1 over x2 minus x1. Okay, so what you need to do now is we need to find the function value at those points. So we know the coordinate points we know the point 2, we want to find what it is on this axis. We know point 3, we know at x is 3. Okay, we want to find what it is on this axis. So what we do is we put 2 back into the original equation, and we get 18.04. So if you go across there, that's about 18.04. And we put 3 in the original equation, we get 22.56. So what we have now is the coordinate points of that line. And so if you want to find the average rate of change, we just put y2 minus y1 over x2 minus x1, and that comes up to 4.52. What we really need to remember, though, is it said here that the money's in thousands of dollars, because it did say explain the meaning of the value you find, and including the units. So that's times $1,000. And X is in millions of units, so that's 10 to the 6 units sold. C, calculate the instantaneous rate of change at x equals 3, x equals 8, and x equals 13. Explain the meanings of these values. If we want to find the instantaneous rate of change, we use the derivative. Okay, so the first thing we need to do is from the original equation, we need to find the derivative equation. So that's 3 times 0.08 is 0.24. 2 times minus 1.9 is minus 3.8 x. And this one just becomes 12.5. Okay, if you're unfamiliar with what we're doing here, go back and have a look at the textbook, how to find the derivative of a function. Then we put 3, 8, and 13, 3, 8, and 13 to find, that will give us the slope, the gradient. It'll also tell us if it's a negative gradient or a positive gradient. And at 3, we find it's positive, so it's a positive slope. At 8, it's a negative number, so it's a negative slope. At 13, it's a positive number, so it's a positive slope. So that's what we're finding from those values. D, state the values for which the instantaneous rate of change is positive. State the values of x for which the instantaneous rate of change is negative. Explain the meaning of each of these results. Well, we can just look at the graph, and you can see from the graph here that it's positive up until that point, then it's negative to that point, and then it's positive. So if you break that up, between 0, and by the way, I've used, the book didn't seem to use it, but I've used the restricted domain. So I've got x greater than or equal to 0, so from x all the way up to that point right there, which is x is 4.66. That's positive slope. It's also a positive slope from this point here, which is from 11.2 up until 15, because we stopped it at 15. So that's where it's positive. Now, where is it negative? It's negative here, between that peak and that trough right here. So where the maximum and the minimum, we know that's 4.66. So x is greater than 4.66 and less than 11.2. And that's why I've got the negative there. E, write down the values of x for which the instantaneous rate of change is 0. Justify your answer. Well, this occurs where the derivative is 0, and so that's at 4.66 and 11.2. It's at that maximum and that minimum. F, find the maximum and minimum values and show that these are maximum and minimum values. So what you do is you put the number for 4.66 in here, and then you put that into the original equation here to find out what that number is going to be, and it's 25.1. Okay, that's the maximum value of the function, a local maximum. And then the other thing you do is you put 11.2 in there, and you find the function value at 11.2. But remember, you must use the original function, and you find that as 14.1. And that's a local minimum. Okay, well, it might be worth to investigate, however, that we were given this restricted domain, so there's a minimum over here, obviously. That's 0. Okay, that's a minimum. Between 0 and 15, it's a minimum. Also, what happens over here? That's 15. So if you still have this in your calculator, just put in x equals, well, you can put x equals 15 in there and find out what the function is and see if it's higher than this 25.1. Is that really the highest between that restricted domain of 0 and 15? That would be worth investigating. 3, the path of a shot put can be modeled by the function, this function where t is the time in seconds and the function is the height of the shot put in meters above the ground. Find the maximum height of the shot put and the time when this occurred. Well, I put it straight in the calculator, and as the graphic display calculator, and then I did analyze graph, and I found this point here, 6 and 4, and therefore the maximum height was 4 meters. Remember, because the vertical axis is the height, and this here is the time, and so the time is 6. That's why it's 6, 4 there. So that was a quick one. 4, the profit P that Yarona makes each day is dependent on the number of brownies and that she bakes. Her daily profit can be modeled by this function. Find the maximum profit that Yarona makes in a day and the number of brownies she needs to sell to make this profit. Well, again, I just put that straight in the calculator and I got that. I used the analyze graph function to find the maximum, and therefore the maximum profit is 120. I think the book is wrong on this. I think they've got 50 and 50, but it's 120, and so that reads off there to 120, and this is 50 here. So the number of brownies to sell to make this profit is 50. So that was also a quick one. Question 5, a business buys engine parts from a factory. The business is currently deciding which of the 3 purchasing strategies to use for the next stage of its development. Its researchers produce models for each of the strategies. P is the expected profit in 10,000 euros, and N is the number of parts it buys in thousands. The largest number of parts the factory can sell to the business is 5,000, and there is no minimum. A, for each model, find the maximum profit and the number of parts the business needs to buy to make this profit. So what they told us is the largest number of parts the factory can sell to the business is 5,000, and there is no minimum. So why don't we put 5,000 into these equations, but remembering that N is in thousands. Therefore, I'm going to use a 5. So here we put a 5. And we calculate the profit when N is 5, which is equivalent to 5,000. And we find that the profit here is the answer is 4.6, but we need to remember that it's in 10,000. So that's 46,667 euro, 51,667 euros, and 45,833 euros. So if you just looked here and you just assume that that would be the best profit because we buy 5,000 of them, well, that would be true if it was linear, but what we've got is we've got different shape functions. So what I did was I put that into the calculator and I got that. I put this one in the calculator and got this one, and I put that in the calculator and I got that graph here. Now, remember, we're only interested in the first quadrant. Let's see what happens. Now, interestingly, this is obviously a straight line here, so the more parts, and only up to 5,000, but the more parts would give you, well, up to 5 really on the graph, and the more part, that would give you the profit, right? And it looks kind of linear. Now, this one here, there's a peak, and then it drops down again. So that's interesting. And this one is the same. Now, if you analyze this a bit further and you use the analyze graph function to find out where that maximum is actually at 4, which is equivalent to 4,000 parts. And the profit is 4.66, which is equivalent to 46,667 euro. Okay, so it looks like strategy 3 is the best one. And state which strategy it should adopt. This one. Now, if you go back and have a look at this peak here, this happens at 2,000, and the profit would be around 6,000 euros at that point. Okay, so that's why this is the best strategy. Again, in the back of the book, they say that one. That's because they've interchanged those two. 6. John is a keen cyclist and is planning a route in the Alps. The profile of the route he would like to take can be modeled by this function, and that's the restricted domain there, where y is in hundreds of meters, is the height of the point on the route that is a horizontal distance, which is x, which is in 10 kilometer units from his starting point. Plot the graph and find the maximum height John will climb on this route. So we just put that straight in the calculator. The domain was restricted to 6. So I've actually looked at the 0. So when you do analyze graph, put the maximum there, find the maximum. You've got the maximum x here and the maximum y. And here, I wanted to find out where it crossed because I need to copy this into my test paper and I need to copy the main point. So you'd need to copy, you can't include this point because it says you've got up to 6 only. So if that's 6.29, you want to make sure you stop around here. Okay, you're just going from 0 to just about here and you want to stop there. Don't go down to this point here when you're copying it into the test paper. Okay, and look, that came straight out with the answer. They told us, all they wanted was the maximum height. This y value measures the height. It was 3.91742. It's in hundreds of meters, so that became 392 meters to 3 significant figures.